All right, everybody, welcome back here one more time. A quick chemistry lesson. Let's talk about gases. Why not? So, obviously, when we're talking about gases, we're talking about a state of matter where pretty much everybody's broken apart from each other. They're flying around, they're causing collisions. As we have collisions increasing those collisions, we do see an increase in pressure. If the collisions go down, we do see a decrease in the pressure. One of the units of gases that we measure is pressure, and there's some common units associated with it. I would say 1 atmosphere is a very common unit. That is equal to 760 mmHg. Does stand for millimeters of mercury, as that is what a barometer used to be made out of. Maybe still made out of that as well. Also equals 760 torr. Torr named after the guy who invented the barometer, which measures atmospheric pressure. A millimeter of mercury is equal to 1 torr, so it is a 1-to-1 relationship between those two guys. Now, I would say probably if you're watching this and you're taking chemistry, these are probably your big 3 units that you most likely will come across: atmospheres, millimeters of mercury, and torr. There clearly is other pressures units like psi, pounds per square inch. There is bar, which is another very common one. There is pascals or kilopascals are also another units of pressure. But like I said, probably these are your big 3 right here. And that 760 number is an important number. If you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by that 760. We'll just use torr here. And atmospheres would go on the bottom, setting up a little dimensional analysis like we've been talking about in these videos. A link in case you missed those earlier ones. We've been multiplying what's on top there, dividing what's on the bottom. Again, you could think of it like a fraction, if you will. Dividing atmospheres by atmospheres cancels and gives you torr. If you're starting with torr or millimeters of mercury, either one, because they are basically a 1-to-1 conversion there, you would actually divide by the 760. And the atmospheres would go on top. Once again, we're going to multiply on top there, divide on the bottom. Torr or millimeters of mercury will cancel, and we'll leave you with atmospheres. So when we talk about gases, we oftentimes talk about gas laws. And there are a number of gas laws that we come across. When we talk about these gas laws, there's kind of 3 variables oftentimes we deal with, which is pressure, temperature, and volume. So there's a number of gas laws to look at all 3 of these, or 2 of these guys along the way. So let's talk about the first one, which is our friend Boyle's law. And Boyle's law dealt with the pressure volume relationship and held temperature constant. And basically Boyle's law is P1V1 equals P2V2. This again is at constant temperature. And what we see in this case, or what Boyle saw in this case, was as the pressure went up, the volume went down, and vice versa. As the pressure went down, we saw an increase in the volume. So we just think about it logically. If we have a small volume and we got gas molecules in there, pretty good chance going to start having a lot of collisions. A lot of collisions going to see that pressure increase. Now, if we give everybody a little bit more room to fly around in and increase the volume, It's going to take longer for those collisions to occur. The result of that is less collisions, and we start to see a decrease in the pressure. Now, in terms of units here, pressure can be any unit you like. Volume can be any unit you like, as long as they are the same units on both sides. So if you have a pressure that's in atmosphere for number 1, and you have a pressure that's in millimeters of mercury for pressure number 2, that's not going to work together. You got to choose. It doesn't really matter which one you choose. They do need to be the same. Same thing with the volumes. They also need to be the same unit. So that's really important along the way. Now, the next gas law is our friend Charles' law. Charles' law. Charles looked at volume and temperature and held pressure constant. So his gas law was V1 over T1 equals V2 over T2. Once again, this is that constant pressure. Now, when we look at Charles' law and pretty much any gas law, temperature, really important, pretty much a no-brainer. It has to be in Kelvin. Reminder to get the temperature in Kelvin. You take the temperature in Celsius, you add a 273 to it. True number 273.15. Most people just use 273. But pretty much if you have a gas law and you got temperature, that should always be in Kelvin. Even if they ask you for the answer in Celsius, they give you the temperatures in Celsius, you need to convert it to Kelvin before you go into a gas law, pretty much always. Volume here doesn't matter the units as long as they are the same volume units on each side. So what happens here with Charles' law? We always think about it. So in this case, this is actually a really important aspect of it, which is the constant pressure. So what we see actually in Charles' law is as the temperature increases, so does the volume. And as the temperature decreases, so does the volume. Why is that? Well, let's think about it. If we have a container such as this with some gas molecules in there, be for good luck, and we decide to increase the temperature, what's going to happen to those gas molecules is they're going to fly around a lot faster. And they're going to fly around a lot faster because they have more energy. That would cause more collisions, and we would probably expect to see the pressure increase. But in this situation, we don't want the pressure to increase. We want to keep it constant. So it's actually the volume adjusts, and we see an increase in the volume. So even though these gas molecules are moving around faster, they now have a lot more room to fly around in. It's going to keep the number of collisions relatively constant. And that is how we keep constant pressure. Same thing here. If we started with our original guy and we lowered the temperature, what's going to happen in this situation? I'll draw a new box here. If we lower temperature, it's going to be moving around a lot slower, which means we would expect to start to see the pressure decrease. Again, we don't want the pressure to change. So what happens in terms of the volume is dramatically drawn smaller. We actually decrease the volume when we decrease the temperature. So even though they're moving slower, they have less of a traveling area to go into, and they'll have the same amount of collisions. So in that smaller area, we'll maintain the same number of collisions. Once again, maintains the pressure here. So that is Charles' law. The next law, which is very similar to Charles' law, is gay-lussac's law. And gay-lussac looked at the relationship between pressure and temperature. And he saw P1 over T1 equals P2 over T2. And once again, I see temperature, and then I should always make sure Kelvin is what we're looking for in terms of units. So what did gay-lussac see here? Well, he saw kind of what we just were talking about a second ago. He saw that as the temperature increased, so did the pressure. And as the temperature goes the right way there, draw it that way, the temperature goes down, so did the pressure in this case. By the way, this is at constant volume. Unlike Charles' law, where the volume is going to move, this is a rigid container. We're going to get no movement of the volume, which means if we have gas molecules and we increase the temperature, they're going to fly around a lot faster, causing a lot more collisions, and we're going to see that pressure increases. Here again, the volume is not going to adjust to allow it to stay constant pressure. So we do see that increase. Same thing here. We had our gas molecules in this rigid container. We lower the temperature, going to be flying around dramatically drawn here a lot slower. And because they're moving a lot slower, we will have a lot less collisions and we'll start to see our pressure go down. So this is gay-lussac's law. Again, basically, pressure can be any unit on either side as long as they're the same. Once again, temperature needs to be in Kelvin. So what comes next? Well, it's everybody's favorite, Avogadro's law. That's right, he had a number. Why should he not have a gas law? Good point. Now, when you think about Avogadro, probably moles comes to mind. And no surprisingly here, Avogadro's law involves moles. It is V1 over N1 equals V2 over N2. This is actually at two things. This is at constant temperature and pressure. So constant temperature and pressure, we have Avogadro's law. N is moles. So that is the moles of the gas. V obviously here is volume. And what he found was that the volume of a gas is directly proportional to its number of moles. So this is Avogadro's law. It involves volume and moles. Now, putting all those gas laws together, you got your Boyle, you got your Charles, you got your gay-lussac's, you got your Avogadro's law. You put all those guys together, gives you the granddaddy of all gas laws, PV equals nRT. That is the ideal gas law. This is different than the other gas laws. We had like two pressures, two volumes, kind of like a before and after situation. This is a one condition here, no two volumes, no two pressures along the way. This is also most restrictive in terms of units. P is pressure, which has to be in atmospheres when you use this equation. Volumes in liters, which is what it has to be. N should be moles. And again, our gas law with temperature should be Kelvin. The reason for all this is R. R is a gas constant, and it is 0.08206. It has units of liters times atmosphere divided by Kelvin times mole. So if you have R given to you, you'll actually know the units of everybody else in the ideal gas law. It needs to be those, so everything properly cancels out. Now, when we look at this, we can also have a relationship that sometimes happens, which is STP, and that stands for standard temperature and pressure. And when somebody is given a problem where it says at STP, they are actually giving you those values. The temperature value is 273 Kelvin, or 273.15. the pressure is 1 atmosphere. So those are the actual values when you're at STP. Now, you can always use the ideal gas law at STP conditions, non-STP conditions. Again, if it's not 273 in 1 atmosphere, it's a non-STP conditions. And if it is at STP, you could just simply throw those values into here. Now, there is sort of a workaround. If you are at STP, 1 mole of any gas will equal 22.414 liters, and this is only at STP. So that's sort of a conversion factor that you can use if you're at STP, and you actually can avoid using the ideal gas law. Now, you could always use the ideal gas law regardless and avoid this conversion, but this conversion here, I'll box it, should only be used at STP, never ever outside of that. So always STP. Now, one last gas law here on this quick video is our combined gas law. Now, our combined gas law is P1V1 N1 T1 equals P2V2 N2 and T2. Now, when we do this, this deals with gases, pressure, volume, and temperature, and N is moles. Usually the moles stay constant, and you will oftentimes see this one as P1V1 over T1 equals P2V2 over T2. Now, this is what is usually commonly referred to as the combined gas law. The temperature here, like normal, Kelvin. Pressure can be any unit as long as they're the same. Volume can be any unit as long as they're the same. So when we talk about these gas laws, let's talk about a couple of things. First off, how do we get to that right there? That's actually from PV equals nRT under 2 different conditions, kind of like a 1 condition and a 2 condition, and solving for R would equal P1V1 N1 T1 if these were all 1s. I'll put them in there. And these are all 2s, obviously, in this case. And if we solve for R over here, this would be our P2V2 N2 T2. And R here and R here is a gas constant, which means we could actually set these guys equal to each other. And that is how we get to this equation right there, by the way. Now, when we look at gas laws and we need to rearrange these equations, let's just take V1 T1 equals V2 T2. Now, whenever you move something across the equal sign, they always end up in the opposite location. So this guy would go down, this guy would go up, this guy would go up, this guy would go down if you needed to switch around. So if you had V1 T1 equals V2 T2 and you want to solve for V2, this guy on the bottom, which is T2, needs to go to the other side. It ends up on top. V1 T2 T1 equals V2. Now, if you had P1 V1 equals P2 V2 and you want to solve for pressure P2, although it's not written as a fraction, you can think of it like a fraction, which means they're both on top. We want to move our V2 to the bottom, and that gives us P1 V1 V2 equals P2. So that's how you could quickly rearrange these equations. If you had P1 T1 equals P2 T2, and we actually want to solve for T2. In this case, whatever you want to solve for needs to be on top by itself. That means we need to move this guy to the other side. So that would get us P1 T2 divided by T1 equals P2. Now that I have this guy up on top by itself, or not really by itself yet, but it's on top. I can now move everybody else to the other side. Change the colors so you can kind of see it. That means the P1 will have to go to the bottom. The T1 would go to the top. And that would give you T2 is equal to P2. We moved T1 to the top and we moved P1 to the bottom. So that's how you could quickly rearrange these equations by moving things in opposite locations. So wherever they go across the equal sign, they will end up in the opposite location. So this is a lot of gas laws. So let's be honest, it's a lot of gas laws. Who wants to remember them all? I know what you're thinking to yourself. You don't really want to remember them all. So what can you do? Well, if you had to invest your time into remembering a gas law, this would be the one. And this would be the combined gas law. And it would actually be the combined gas law that we got from the ideal gas law that we used twice, basically, the one we just did on this previous slide. And that would be the one where we set them equal to R. It's equal to PV over NT. And this guy would be equal to PV over NT. Again, taking these two guys and dividing them to the other side. That would give us our basically P1 V1 N1 T1 equals P2 V2 N2 T2. So why is this one really perhaps the best one to remember? This is why. You pretty much, if you remember this gas law right about here, you could get every single gas law pretty much we just saw on all those previous slides. So how do you do that? Well, you come across a problem and it does not mention anything about moles. It does not mention anything about temperature, or they tell you it's held constant. So all you have to do is come to this equation and go, I didn't hear anything about moles. I'm just going to cross that out. I didn't hear anything about temperature, or it's held constant, it was told. I'm going to cross that out. And look at that right about there. There is Boyle's law coming out. Now, if you take this equation, again, this sort of combined gas law equation here with the moles in it, and you come across a problem and they say nothing about moles. So you go, okay, no moles. Scratch that out. They say nothing about pressure. Okay, let's just scratch that guy out there. Pressure on each side, we're scratching out. And now we are left with Boyle's law. We take the combined gas law there. And you read in a problem, and again, no moles, so scratch. And no volume in this problem, or it's held constant. Scratch it out. There it is right there. If I didn't scribble on it there, that is our gay-lussac law. Fix that a little bit there, get my eraser. I got rid of my whole box, that works. For a better box, take two. There you go. Now, hey, you got this one here, P1, V1, N1, and T1 equals P2, V2, N2, and T2. And you read and they go, nothing about pressure, nothing about temperature, they're held constant, so no pressures. All right, get rid of those. No temperatures. Ready? Get rid of those. There it is. There is our Avogadro's law. So this is basically all the gas laws at your palm. All you have to do is scratch out and get rid of anything that's held constant, anything that's not given to you in the problem, and you'll be left probably with the gas law that you need to use. Then you're thinking to yourself, well, what about the ideal gas law? Well, if you still remember this, which is P1 V1 over N1 T1 equals P2 V2 N2 T2, and all you have is one pressure, one volume, one mole, and one temperature, then you can just scratch out this side and just remember that is equal to R. And now you basically got your PV equals nRT back. So that is a good way to get there as well. So if you want to invest your time, probably the combined gas law there with the moles in it is the one to remember, because again, you can just scratch out what you don't need, what is held constant, and you'll have them all. And if you want to just be safe about everything, you go for the 2 here, and you'll pretty much have every gas law you would ever need to use right there at your fingertips. All right, I think actually we're just going to lay it up right there. It's kind of turned into just an overview of the different gas laws and hopefully a quick way to get to each of those gas laws to use them. I hope it helped. If you'd like to hear about any other chemistry topics, just let me know in the comments. Thanks for watching. We'll see you on the next one. Bye-bye.